It looks like not everyone has woken up. I think we can wait 2 or 3 more minutes and then we will start.
Okay, no problem.
Hello.
Hi, Vika. Hello, this is Matvey speaking. We have more than 30 participants from both sides. Good morning to European part of the continent. Good evening to Asian part of the continent. I'm happy to see 32 participants from both countries. We're starting our 12th seminar of UniCFD, which is a joint workshop of 2 teams: Ocean University, College of Engineering, and Open Source Software Laboratory of ISP RAS. The collaboration between our teams started about 1 month ago to training track inquiry from Dr. Qin Zhang. After several conversations, we came to understanding that our team could augment each other if we unite our efforts in numerical simulation for oceanology applications. So the aim of this workshop is to get acquainted closer. For example, the Ocean University team is strong in physical experiment and numerical simulation, and whereas ISP RAS team is more focused on software development and numerical methods. I hope the workshop will be productive, and as a result of our discussion, numerous ideas for cooperation will emerge. The workshop is organized as follows. First 1.5 hours are occupied by talks from Ocean University. Then we will have a break for 1 hour. After that, workshop continues with presentations from ISP RAS. And finally, the workshop wraps up with 30 minutes discussion. Each talk should not exceed 20 minutes. We have to keep this time limits. And we have 10 minutes for questions after each talk. Our first talk by Dr. Qin Zhang, numerical analysis on the wake dynamics of a ducted propeller under a flat plate. Dr. Qin Zhang, please. Dr. Qin Zhang, we don't hear you.
Okay. Oh, you can hear me now, right?
Yes, yes, we can hear you.
Okay, good. Let me share the slides. Yeah, you can see the slides now, right?
No, only black screen. Yes, now I can see your slides.
Okay, thanks. Okay, thanks everybody. And we're talking. In this seminar, I want to talk about my current work about thruster and the weak dynamic of the thruster with simulation with OpenFOAM and some of our results. And we like to hear your opinions and how to do the next step of our work. So we have several contents I want to discuss. First is motivations. And the motivation, mainly two parts of motivations. One part comes from the offshore industry. For the dynamic positioning system, is a DP system. And for this DP system, it normally have a 6 to 8 thruster. 6 to 8 thrusters. And this thruster will point to different directions to maintain the submersible platform at one position. So this will encounter several problems. One is thruster hull interactions, and another one is because they have several thruster working together. They might have thruster interactions, and also induced flow-induced vibration noise. All these are concerned by offshore industries. And this part of motivation. Another part of motivations is about another part of motivation is about all the propeller or thruster wash scale. And you can imagine if you have a ship or vessel, and in the harbor, you can think about this thruster or propeller or core wall interactions. And if we have a slope bank or brick waters, we also have this kind of interactions. This propeller weight or the jet flow might be scale the seabed and cause the damage and makes the water breathable. And also, if in very shallow waters, we also concerned about this seabed scale. All these kind of scale and DP system, they all concern one thing is the thruster hull interactions. So that's what we try to do right now. And first is our research target. First is our research target. We are using the marine thruster GIP thruster joint industry project model thrusters. And this thruster only have 100 millimeters in diameters. It's have a 4 blade. The RPM is around 1,000. The reason we use this thruster because this may be the only one we can find published, especially they use PIV to measure the wake dynamics. This is ideally for us to do the validations. That's why we use this one. Also, currently we are building our abilities about this PIV and thruster facilities, thruster test facilities in our university right now. First is the domain, a computational domain. We use cylindrical domains, and we use a full structured mesh. And think the difficult part is difficult part for the meshing is the gap between the nozzle and the blade. We know in OpenFOAM, even if we want to use the MRF method or AMI method, we need to have a interface, and this interface between the rotation regions. And unfortunately, in thrusters, we have a nozzle, and this nozzle is definitely in the stationary region, but the blade is moving. So we have to have the interface between the blade and the nozzle. And for this physical gap is already very, very small, and we still need to divide this physical gap into two parts. So that might be the most difficult part for the meshing. Finally, we achieve it and generate the mesh. Because we want to investigate the weak dynamics, we want to see more details about the weak. So we generate a relatively big mesh for the stationary region, especially for the weak of the thrusters. And also, we are not only conducted some thruster tests with the axis flow, we also investigate oblique flow. And of course, the thruster underneath under a flat plate. And this one is identically with Marine's physical test. And the method we use, the numerical models we use in OpenFOAM, the first one is for the stationary simulations. We are using the multiple reference firm. It's quite common. For the dynamic mesh, we are using AMI in OpenFOAM. The reason we want to start from MIF is there are several reasons we want to start simulation with MIF. First, MIF is quite fast and it's quite mutual in OpenFOAM. We can just use a simple form to start the simulations, and it's quite a cost efficiency. It's from our experience, biggest mesh you have, you will get the result in 24 hours. And most important is for MIF, they have a very good accuracy on force calculations, especially for the design conditions. What I mean design condition is like in access flow. It's the result is very close to experimental data, but the bad side of this MIF is because it only can give you a wrong weak flow. If you want to investigate weak flow, MIF is definitely not a good choice. So we use the MIF as a start point, and then based on the MIF result, we initiate this AMI transient simulations. First, use the RAMS model, Spala-Alamanus RAMS model, and later on, we use the Spala-Alamanus model. We use these models, it's because this is one of the original Spala-Alamanus model for DDES. We know they also have a K-omega SST DDES models, but we prefer to use the original one. And maybe later we can try K-omega SST DDES model to see whether there is a different. And also we prefer to use DDES model instead of DES model, because for DDES model, this is a delayed detached eddy simulations. This forced this solver forced the RAMs resolve regions only close to the wall. And for our thruster case, we have many walls in it, so it might be perfect for this our thrusters. It might be some kind of balance between the accuracy and calculation time. Because I'm using OpenFOAM class 3.0 for the first case, So at that time, it's a pimple divide form. Now, for the newest versions, they already emerged with a pimple form. You can directly use the pimple form to conduct the simulations. And we successfully get a very detailed weak flows with this AMI and the DDES model. I will show you it. First, is a model validation, of course, and the left one is MI study simulations, mesh sensitive studies. I mentioned is the result is very close to physical experiments. And the right one is transient simulation. Here are three figures. The first one is the RAMS result, and the second one is the DDS result, and the third one is the PIV result. I have to mention for this, even we get some PIV test result, but the test result is still, the physical test result is still not that perfect. They cannot provide or they cannot capture the instantaneous velocity regions. They can only capture the average, so-called average flow. So it's showing, actually it's showing some average flow. I mentioned the so-called average is still not that kind of average. It's some kind of the measure these velocities in 28 seconds and get maybe 100 or around 100 snapshots and average this 100 snapshot. And we basically use the same way to extract our data and do the comparisons. And we can see for the RAMS model, it's trying to give you some kind of average result. And for DDES, we can even we average it, we can still see some unstable. It's more close to the physical experiments. And first, I want to show some MF result because I mentioned MF is perfect for force predictions. And we done some open propeller test and with faster or ducted propeller test. It's mainly the propeller itself is same, is exactly same. Only one case with a nozzle, another case without a nozzle. And we can see this is the propeller performance. The G is so-called advanced coefficient, is a non-dimensional number related to velocities and RPM. And of course, the propeller diameters. And the left one is force. We can see for this red line, this red line is for open propeller without nozzle. And we can see for the green one is actually the propeller force inside the nozzle. The other one is a propeller nozzle force. Combine this, you can see although with nozzle, the propeller thrust force is reduced, but because we still get additionally for thrust force from nozzle, we still get a much higher thrust force compared with simple compare with the open propeller. And that's also explain why thrusters or ducted propeller have a better performance compared to only single propeller. And that's why more and more vessels like submersible platform or even some commercial vessels, they turn to use thrusters. They turn to use ducted propeller instead of normal propellers. And also we try some case with oblique flow, oblique inflow. And we can see when advanced coefficient increase, the nodal force will increase faster than the propeller force with the increase of inflow angles. These are all MIF results. Actually, from my point of view, this results because it's some kind of off design conditions. And we already done some AMI simulations or transient simulation with oblique flows. And we prefer to compare all the MIF and the AMI in these off design conditions. I guess there might be some difference. And also this pressure force for the oblique flow. We can see the side, the contour looks so similar for different angle or different advanced coefficients. But for the section size, you can clearly see some effect of the oblique flows. And if you saw this nozzle, I divided this, the nozzle in one and outside one. Inside one is close to the propeller blade. Outside one is just close to the far field. And I rolling into flat, rolling the pressure contour into flat to plot these figures. Now we can see for the inside, only at a very high advanced coefficient and high inflow angles, we can see some effect. For inside is demonstrate how nozzle as a shield for the blade. But for the outside, we can clearly see this oblique flow effect. This for the MIF result. And for the AMI result, the calculation procedure is a little bit more complicated because we either want to accelerate our simulation because it's always a big simulations. And on the other side, we also want to get as accuracy as we can. So the procedure is working like this. We use MIF to generate a very coarse initial conditions, flow conditions. And in these flow conditions, we initiate ramps simulations. And for maybe about 10 revolutions. After 10 revolutions, this weak flow, we can generate roughly a coarse weak flows. And based on these weak flows, we we initiate this DDES model. And also to save the computational time, we first use a coarse mesh, is a 30 millings mesh to go through these procedures. And then in the final procedures, we mapping this result to a refined mesh. Have the DDES again in a refined mesh. In here, we try to use a 240 CPU cores to run one case. It's it's about roughly about 1 revolution with 2 or 3 days, something like that. And because we have a very small gap between the tape between the propeller tapes and the nozzle, and in this small we also have a interface. We also have a rotational region and a stationary region. That makes the mesh at the propeller tape very, very small. So that's the reason we only can get a Prandtl number around 7. And also the time step is very, very slow. It's about 10 time step per degree. And we run 4 cases with the increased advanced coefficient. And this is phase average result about UX for 4 different flow conditions, in-flow conditions. And you can clearly see for the weak, for this ball condition 1 or no inflow velocity ones, and the weak is relatively short. And but for the high velocity ones, we can develop quite far. And these figures show you the magnitude of vorticities. It's mainly demonstrated the vortex structure development. And for the ball conditions or the inflow, zero inflow conditions, these vortex structures develop quite complicated. And we zoom in. This one is the zoom in one. If we look more closely, we can see, we can clearly see this. This not from in here. This is not tip vortex. This tip vortex. If we don't have a nodal, we will have a tip vortex, perfect tip vortex. But in here, because we have a nodal, this nodal attracts some energies from this tip vortex. Only some of this vortex leaks from the nodal. So in here, we so-call it tip leakage vortex. And this shows you the kinetic energies about 4 cases. The kinetic energies reflect the total energies about this flow. And the total energies is also includes the inflow energies. So we can see for the case 4, they have most energies. And if we remove the average values, we will get the turbulence kinetic energies. And this demonstrates how turbulence strongness and the turbulence intensities is quite, we can see the comparison is quite clear for the zero inflow velocities case. They have most complicated or most strong turbulence kinetic turbulence development. And here's some instantaneous result with vorticity magnitude vorticities, and this showing it in isosurface mode. Only half of these vortex structures. Again, we can see more clearly about this turbulence. If you see, we can see this tip leakage vortex, this helix vortex. Also, there is a blade wake generated from the blade. And we try to use volume rendering to reconstruct all this flow. And from volume rendering is basically use the transparency to put more transparency on the not important vortex structures and put less transparent on the most serious or most important flow structures. So we can see the important structures more clearly. And now we can see several interesting turbulent structures. And the first one is leapfrogging vortex, as the to another small and 2 vortex tube climbing with each other, like leapy flagging. And this one is quite obviously in the zero inflow conditions. And also when this for the case with the inflow condition, also with more inflow conditions, these tip linkage vortex structures will be maintained much longer, and we can have the second flow turbulent structures like shortwave instabilities this actually short wave vortex structures, and when it's become unstable, we call it short wave instabilities. There are three types of instabilities. One is short wave, another one is long wave, another one is molecule-induced instabilities. For our case, we only observe this short wave instability one, and all these mean vortex structures or turbulent structures will eventually turn into small scale. Before they turn to small scale, they first turn to secondary vortex, like this short wave tube. First turn to a secondary vortex, and eventually it will go to a very small scale vortex in the far field. And this demonstrates these animations for volume rendering. We can see this the leapfrogging, and for the other ones, we can see this short wave. We can become short wave in first is a perfect helix structures, and later on is become the stable style is like a short wave is stable, and then into the secondary vortex, eventually go into a small scale vortex. And we also put tons of probe in the wake to monitor the velocity of pressures, and this result looks like. We can see there's a two velocity region in the wake. It's not actually not two high velocity regions because we only cut a slice. It's actually a high velocity ring in the wake of the propeller or thrusters. Especially for thrusters, this ring is more thin and more strong. You know, this one is showing you some probe result with FFT. We can clearly see these blade frequencies is the domain frequencies, of course, because there's nothing in the front yet. If we put the thruster in the back of the boat or back of the vessels, this signal will turn to different. And also, I only roughly show you some initial results for this oblique flow. And the left column is the ducted propeller, the propeller with nozzle, and the right one is a propeller without nozzle. Identically same propellers, only with nozzle and without nozzles. And we can clearly see the nozzle actually some kind of protect the propeller blade. And if we without the nozzle, we can see a more strong or more violent the way. And this is some result for the thruster underneath the blade. We conducted 4 cases and 2 cases with a 0 degree angle. It is actually parallel with the thruster parallel with the blade with 2 different advanced coefficients. And also another 2 cases with a 7 degree angle. And this 7 degree angle is recommended by industries, and they conducted some research and come out that this 7 degree or 9 degree can significantly reduce the conduct effect. And that's the main effect. This is one of the main effects for this thruster Hall interactions is that it will dramatically reduce the thruster performance. So without they can get a better result. Now they can get a better performance. So we try these 2 cases to see whether it's true. And this one is also the magnitude vorticity. Magnitude vorticity with the phase average result. And the most interesting part is actually the top two case. I mean, the case without flow is four-pole condition case. And the case, the case without inflow is quite common for this DP system. Because I mentioned before, for this DP system, the 6 or 8 thruster try their best to point at different directions to maintain the submersible platform stay in one place. So most of time is working in the zero inflow conditions, and in the zero inflow conditions, quite interesting flow structures. And if you're working on aerodynamics, you might be familiar with this vortex, and this we call it ground vortex. And this one is previously, as far as I know, this one is only report or concerned by the aerodynamics. I haven't seen any literatures to mention this also what happened in offshore industry. It's quite interesting. Even we get a different angle, they still can get some ground vortex, but maybe a little bit weak. And if we zoom in to see it, this ground vortex was such a flow on the near this plate. Is have a threaten to in the aerodynamics is have a threaten to the engine, but I think in offshore industry can be a potential threat to the thrusters. Later on, we may try to spend more time on these vortex structures, to this ground vortex. This for this thruster on the plate. And also this animations, I show it in the last seminars. And we also can see for this flat case, for this 0 degree case, the propeller parallel to the flat plate. We can see some of these flow structures trapped by the plate. And also some people call it, this is actually the conduct effect. But for this 7-degree angle case, this conduct effect becomes weak, but still exists. And also we can clearly see this ground vortex in here. For the 7-degree case, the ground vortex even looks more complicated. And this is the last one I want to mention, the last but not least. We try some works on this weak dynamic analysis with the DMD, dynamic mode decompositions. And this work haven't been finished, and I just show you some initial results. And we try to use a standard DMD code, this code writing in MATLAB, and we try to use 4 revolutions in totally with 1,440 samples. And for this kind of work, one of the technically difficulty part is how to efficiently utilize the memories, because we all know for these DMD simulations, these memories, the computer memories, this might be the main concerns, because we need to put all the data into one tree, one map tree. And also I heard some people develop some new method to use less memory, but we still prefer to use the original standard DMD method. So we spend we spent some time to modify this MATLAB code, because for this DMD method, there are a lot of standard MATLAB code we can easily to find. But we modified this code to use the minimum memory kind of result. And we are still in process to announce this kind of result. And I definitely talk too much. And thank you for your listening, and look for your comments. Thanks.
Thank you. You are a little out of time, so dear colleagues, please, two short questions. Does anyone have questions?
No, just a short question. What was the variable? What was the quantity which you visualized in the previous slides with MATLAB?
You mean this one?
No, just the, yes, here.
This one is the mode we get from the DMD method, and we still what that mean in it.
No, but what is the variable? What is physical? You analyze it with the DMD, but yeah. Initially it's the field of what?
Oh, it's still verticities.
Ah, verticity. Okay.
Yeah.
You don't have problems. It's a very big array of data. You don't have problems with memory when you analyze it in MATLAB?
Yeah, we have a problem with memories. And for this case, actually it's required 2 GB memories to do this DMD analysis. But unfortunately, I done this in Singapore, and we have supercomputers. They have this kind of memory. Yes, memory is definitely a big concern.
Okay, thank you.
On slide 14, you show current number about. Did you use implicit scheme or explicit?
Sorry, I can't clearly hear you. Which question? Could you please repeat your question?
Slide 14.
Why what?
Is about 7.
Can you go to slide number 14?
Slide number 14. Okay.
Yes. Okay.
On this slide, you show that current number is about 7.
Yes.
Why? Did you implicit or explicit scheme? Should you explain this?
Yeah. For this 7, because first thing is because in this ducted propeller case, the difficulty part for the machine is the gap between the blade tips and the nozzle, and the reason we get a quite high current number, I believe, is because there is a very between the gap between the blade and the nozzles, and and also we get a 7 because we want to have a high time step as we can. Even we use 7 current numbers, the time step is still 10 time step per degree. Is a very small time step. And because we use a PIMPO-FOAM, PIMPO-FOAM is allowed us, it's actually one of the advantages for PIMPO-FOAM to allow us to use high current numbers. And we also try to use even higher current numbers, but the simulation is immediately into unstables. So we maintain it at 7s. We try to use lower ones. I know the principles, 0.5 is a perfect one, but we try 0.5 current number, the time step will be very slow.
Okay, thank you. I think we can now go to next presentation. Sorry,
okay.
But we have to keep time limits.
Okay, no, I know.
Okay.
Thanks.
Please,
Thanks.
next presentation by Boyan, development of drift-flux model for hydraulics and sediment dynamics based on OpenFOAM. Boyan, please.
Boyan, we cannot hear you.
Yeah. Hello?
Go.
Can you hear me?
We can hear you now.
Yeah, okay. Hello, everyone. My name is Boyan, and my research interest is mainly related to sediment transport. The title of my report is Development of drift-flux model for hydraulics and sediment dynamics based on OpenFOAM. I mainly introduce two kinds of numerical models that can be used to simulate sediment transport in OpenFOAM, the single-phase model and the drift-flux model. In single-phase model, the is treated as volumetric concentration, which is passively transported with the water flow. The single model is divided into three parts. In hydrodynamic model, the governing equation is Rank's equation, and the free surface is simulated by Wolf model, and the K omega model is used for turbulent closure. In the sediment transport model, the bedload transport rate is calculated by empirical formulas. And the suspended load is calculated by solving this convection diffusion equation. And but there is a problem in solving this equation. That is how to calculate the sediment concentration at the bottom boundary. Some empirical formulas can calculate sediment concentration at referent height. The referent height is generally 2 times of sediment particle diameters above the fluid bed. This formula will give the sediment concentration at the reference height, but not in the bottom boundary. Some people think the reference height is very small, so the bottom concentration is equal to the reference height. But this will be result the gradient error about for the concentration. So there are some ways to try to solve these problems, such as constructing a submesh with reference height as the bottom boundary, and or for unfed mesh, we can assume equilibrium condition between the near wall cell center to the bottom boundary, and then the bottom concentration value CB can be obtained by integrating the distribution of suspended sediment between the cell center to the bottom. However, those methods have some limitations in my tests, such as they need high quantity requirement of the grid near the bottom, and this easily cause the calculation divergence. The bed load change based on the external equation. This equation, the dB and the EB represent the deposition and increment flux at the bottom boundary. And this can calculate from the suspended load model. Finally, we need the dynamic mesh to update the bottom boundary position of the to update the grid point position of the bottom boundary and adjust the point position of the whole calculation domain. The single phase model is tested and validated against the third wave cases. The experiment of the layout of Summers experiment is shown in this figure 1, and the parameter setting of experiments and numerical simulation is shown in this table. The D is the median particle diameter of sediment, and for simulation, 2D numerical wave flume with same slope is established. In the near bed region, the minimum cell center height is set to Y1 is 0.5 millimeter, and the upper part cell height is extended to 5 millimeter, and the upper part cell aspect ratio is kept as 2. Same as experiment, 8 measuring pointers are arranged in breaking and swatch zone, and 2 candles of simulations with different bed types are conducted. The surface elevation and bed shear stress with the rigid bed simulation, and the bed profile change were calculated with sediment bed simulation. The figure 3 and the figure 4 give the comparison of the free surface elevation and the bed shear stress. It can be found from the figure 3. The result of comparison of free surface elevation are satisfactory. The calculated value fits with the experimental value fits well with the experimental value at run down stage, at run up stage. However, in section 1 and section 3, it can be found that there are some significant difference between the calculated value and the experimental value. It's because the section 1 and section 3 near the hydraulic jump region. Due to the overestimate of the free surface elevation, bed shear stress in the hydraulic jump region is smaller than the experimental value. The calculated bed shear stress in swatch zone in the cruise time is bigger than the experimental value. One possible explanation is a large amount of air is entered when the wave breaking, and the air moves rapidly in the run-up flow. For sediment bed simulation, the comparison of the calculated and the experimental value of bed profile change after 4 solid wave cases for the plot in figure 5. It can be found the numerical model simulates the formation and the location of the sandbar and the soft accurately. Even the deposition at x equals 7 is better simulated. But this is not shown in this result. Overall, the numerical simulation result in good agreement with the experimental result. For a single phase model, it has some advantages such as low computational cost, and the dynamic mesh can capture the better surface, the better elevation change accurately, and we can use the Wolf model to capture to simulate some complex phenomena like wave breaking. But there are also high such as because it not really simulated the suspended sediment moment. It didn't consider the it didn't consider the influence of suspended load on the water flow, and the height of the grid near the sediment bottom boundary is too small, resulting in a large aspect ratio of the bottom grid, like this figure. In the bottom, in the area of sediment settling, some negative volume grid will be generated, which will make the simulation unstable. Therefore, in order to solve those problems, we are trying to improve the use drift-flux model. Because the drift-flux model is more suitable for simulate the moment of two-phase mixed fluid. The basic government of the basic governing equation of drift-flux model is derived from Ola model, and the subscript k equal 1 and 2 representing the water and sediment phase, and the subscript m representing for the two-phase mixture, and the UKM is the diffusion velocity of each phase. This is the velocity respect to the mass center of the mixture. To solve the drift-flux model, we need 4 additional models. The first is a Wolf model. This Wolf model is used to solve the settling and diffusion process of the sediment, and the turbulent model we need some buoyancy modified double equation model like k omega k insu model or LES model, and we also need the mixture viscosity model to calculate the viscosity of the mixed solution at different sediment concentration, and the relative velocity model to calculate the sediment settling speed as different sediment concentration. In these 2 models, different formulas are used for cohesive, non-cohesive sand. These formula are selected in relevant articles. In following up study, we will select suitable sediment samples, measure their rheological properties through the physical experiments, and then we'll summarize and improve this model. According to the aforementioned, the drift-flux model can be divided into the 2 parts: the hydrodynamic and suspended load model, and bedload and morphological model. One problem to be solved is the data sharing between the 2 models. This is how to calculate the sediment erosion, and this is also my main work at present. my idea is, let's say this is the sediment. This is a sediment bottom boundary, and this is first cell next to the boundary. And in each time step, the sediment will settle from the cell center to the bottom, or from the bottom enter to the first cell. And so the sediment boundary can inherit from the fixed value FA patch field class in OpenFOAM, and the value is needed to set to the maximal sediment concentration, which is usually 0.65. So the deposition flux can be obtained by manipulating velocity of the sediment and the concentration of the first layer grid, and the erosion flux can be obtained by manipulating the incremental velocity and the maximal sediment concentration. The incremental velocity can be calculated by some empirical formula, and the erosion flux also need to be added to the hydrodynamic and suspended load model as a system. In order to verify the accuracy of the drift flux model, we select the experiment carried out by the National University of Singapore to check it. The experiment is shown in this radio. The upper part of the flume is water, and the lower part is the water sand mixture, and the sediment concentration is 0.007, and an electric 45-degree tilt plant move from the left side of the flume to the right. Compared with the experiment, we choose the drift flux form and drift flux form solver and LES model to simulate the whole experiment process. The motion of the plant. The motion of the plant is achieved by implanting the overset mesh to this drift flux form solver. As a whole, the drift flux form can simulate the process of the experiment very well, except some limitation of the overset mesh itself. It's difficult to simulate the collision of the plant to the collision of the between the plant and the right boundary of the flume. Our next work is to complete this drift model, and then we will carry out a series of physical experiments to improve this model. Okay, thank you.
Thank you, Boyan. Colleagues, do you have any questions? No, no questions? Okay. So maybe we can go to next presentation and we can discuss this presentation later at the seminar wrap-up. Next talk is by Mr. Haoxiang Gong, experimental study on a method of having 1 minute. Wave energy converters array optimization based on target wave spectrum. Sorry, we don't hear you.
Yeah, we cannot hear you.
Oh,
Yeah, we can hear you now.
okay. Okay.
Yeah.
Okay, thank you. Today I'm gonna talk about the experimental study on a method of Heaving Buoy wave energy converters array optimization based on the target wave spectrum. And my name is Haoxiang Gong, and I'm a PhD candidate from Ocean University of China. I'm going to talk about this in these 5 parts. And firstly, we know that grouping wave energy converters into array can greatly enhance the power absorption compared with an individual WEC. So the WEC array deployment is very important, but existing array optimization methods are mostly based on the same WEC units, and we're focusing on the optimization of the geometric layout. And we always call it a device-based method. But actually, because a certain WEC has a suitable response range for energy absorption, wave energy out of the range will be wasted, and only grouping these WECs into an array cannot change that. So in order to improve the power production of a WEC array, unit with different response should be considered to match the energy distribution of the C. So we call it a C-based method. And here we proposed a method focusing on the characteristics of a C to optimize the WEC array. And in this method, our goal is to choose WEC units which are suitable for selected wave frequencies and then group them into a different unit WEC array. First, for the frequency selection, a wave spectrum describes the wave energy distribution over frequencies, and we're considering this Lange-Higgins wave model. And a C wave, or we call it a random wave, can be described as a linear superposition of many regular cosine waves. So it is rational to divide the wave spectrum into several regular waves by selecting some representative frequencies. And here, a Jones-Webb spectrum with a significant wave height 0.15 meters and the peak period 1.37 seconds is given as a target spectrum. And we can see in this figure, the omega low and omega high delimit the range to cover 90% of the total area. And the parameter omega 2 is the peak frequency, and omega 1 bisects the left part of omega 2, and omega 3 bisects the right part. And so we have 3 representative frequencies. We call it omega 1, omega 2, and omega 3. So these 3 different frequencies were selected as regular wave conditions for our unit test. So in this table, we can know that we have 2 parts of the experiment. First part is WEC unit test, and the second part is WEC array test. And in this unit test, we have 3 different regular wave condition and 1 irregular wave condition. And all these conditions, we have the same wave height equals to the significant wave height, 0.15 meter. And the difference between them is the period, or we can see the frequency. And in the array test, we only have 1 test. Also, in the unit test, we have this irregular wave is just the spectrum, the target wave spectrum. So our experimental method is, as I said before, in two parts. For the regular wave experiments, we have a WEC unit with different PTO damping forces and drafts to test and to find the optimal parameters. And the unit is a rigid cylindrical Heaving buoy. And the PTO damp is constant PTO, and draft, we use this setting in different regular wave conditions to find for each condition which is the best parameter. We call the best parameter included the best PTO damping and the best draft. And we find all the optimal parameters under these three regular wave cases by comparing their power. And the optimal parameter will be recorded as the OT1, which is optimal parameter on the T1, OT2, and OT3. And for the irregular wave experiments, we will have three equal buoys with respective optimized parameters. And we arrange them rectilinearly into a three-body WEC array. And for each array, for each buoy, we use the optimal setting in the regular wave experiments and to test them. For the first one, we have the unit with OT1, OT2, and OT3 for the unit irregular wave test. And second, we have the array with OT1, OT2, OT3. So we call it 1, 2, 3 array, which is considered as optimized setting. And certainly we have the array with 2, 1, just the different order. And last, we have an array, we call it XXX because X represents the best performance in the first test, irregular wave test. And we repeated it 3 times to form an array. And this is the layout of our experiment. And the model test will carry out in the wave current FOAM at Shandong Provincial K Laboratory of Ocean Engineering at a 1:5 ratio scale under fluid scaling. And the fluid is 60 meters long and 1.5 meters deep and 3 meters wide. And we have the buoy, the water depth is 0.8 meters and the buoy is 80 centimeters diameter and height. And for the array test, we have a distance between each array of 3.6 meters, which is 4.5 times the diameter. And okay, the experimental PTO, a PTO system which comprises a tension controller like this, and a hysteresis brake was applied to provide a constant PTO damping. And this hysteresis brake is able to output constant damping torque resulted from a given current input controlled by this one. And to find the accurate relationship between the current input and PTO damping, the calibration tests for the entire structure were conducted using a hydraulic transmission system. We used a hydraulic cylinder installed under the buoy to provide the lift force. The buoy rises with a constant velocity, and when the current input is absent, the mechanical loss force can be estimated by lifting force minus gravity. And the mean value of the mechanical loss force is 19 newtons and was considered constant during the whole experiment. So we can see this is the relationship between the PTO damping force and the current input on the tension controller. And a torque tensor was used to validate the characteristic that the torque generated by the hysteresis brake is constant, and the result shows the curve of torque was an approximate square wave, and the value has an acceptable fluctuation when the transmission shaft is rotating. So this is a physical model, and it's a rigid cylindrical heaving buoy of diameter 80 centimeters and height 40 centimeters. The dry mass of the buoy is 51 kilograms, and we can see this is the structure. 3 bearings were installed at the edge of the buoy to ensure the buoy can heave along the 3 vertical steel bars. And a metal platform, this gravity base, were installed on the upper and lower ends of the bars, respectively. A displacement sensor was fixed on the steel bar attached to the buoy with a wire, and we cannot see it. Very thin wire to measure the heave displacement of the buoy. And also, loads were applied to change the total mass, resulting in the variation of the draft. And the draft of the buoy varies from 10 centimeters to 30 centimeters. And this is the displacement sensor. Sorry. Okay. And these two things, we call it a PTO system, and this is a transmission system. We use this system, hysteresis brake and a torque tensor were fixed on the platform and were connected by a transmission shaft. This, and at the end of the transmission shaft, we have a gear rack structure to convert the torque generated by the PTO system into a vertical damping force applied to the buoy, and the rack was fixed at the center of the upper face of the buoy. And so 3 equal buoys were placed to form a WEC array like this, and every buoy is, we call it the same because we calibrated it before the test to make sure that the current and the input current for each different array have the same PTO damping. And this is a video clip of the array regular wave test. Okay. And here is the result. And firstly, we can see the WEC unit for these 3 tables. Each one represents a regular wave test condition. And this is for the wave condition 1 with this parameter, a second and the third. And we can see that in this table, we have the different drafts and different PTO dampings. And for this condition, we have the best, the optimal parameter for this one is the draft is 10 centimeters and the PTO force is 40 newtons. And we have the best also for the second one and for third one. So we have the optimal parameter for regular wave conditions. We have the OT1, OT2, and OT3 for the regular wave test. And for the irregular wave test, we use the OT1 setting and the OT3 setting to do the irregular wave test, and we have the results. We can see the OT1 setting performed best, and so this one would be applied to group a same unit array. As I said before, the OTX means the OT1 setting. And in the WC array experiments, we found that the OT1, or the 111 setting, we have the total power of this array performs best, and the 1, 2, 3 perform better than the 3, 2, 1. And also, we can see that in this column, we showed the sum of the units, which means that in this one, we have the individual irregular wave test for each setting. And the sum of the units means the sum of the unit in the irregular wave test result. And we can see that when we grouping them into an array, the power production is growing bigger than the sum of individual results. And the increasing rate we have here, and we can see the 1, 2, 3 increase most, and the 1, 1, 1 increase less. Yeah. Okay. And we found that for this one, and compare this one between of this one with the reason of this positive effect is caused by the diffracted and radiated waves within the array. And we found that this reason, we found this is because of the distance between each array, each buoy is 4.5 times diameter, and this range is a positive range for the have a positive effect. And we can see for the 1, 2, 3 array and 3, 2, 1 array, the total power of 1, 2, 3 array was larger than the 3, 2, 1 here. Although the components of these two arrays were the same, but these two figures shows that the power of OT1 buoy from 1.91 to this 1.49 decreased about 6% when switching from the front to the back, and the OT3 buoy only decreases about no. I mean, the OT1 buoy is this between 1.91 to the 1.79, decreases about 6%, and the OT3 1.47 to 1.49 only decrease 2%. And the reason is that the energy of short period wave component attenuates fast with distance, and the energy of long period wave component attenuates slowly. And also, in contrast to the individual unit test, we can see that all these blue ones are taller than the orange one. So when grouping into an array for the 1, 2, 3 and 3, 2, 1, we always have a positive effect. And this is the reason, this is the result of 1, 2, 3 and 1, 1, 1 array. And we can see that although the 1, 1, 1 array extracted most power, but it can be learned from the Buoy C. You can see the Buoy C that with the OT1 setting, it occurred a negative effect on the power output. We can see this one, and it's about 10%, minus 10% compared with the Buoy A with OT1, and about 5% compared with the individual unit result. So this result shows that the power absorption of a buoy in this same unit array decreases rapidly with the increase of unit number and even less than that of an individual buoy. So we have a conclusion here. The buoy unit most suitable for a regular wave with peak period of the given target spectrum may not perform best in the irregular wave because we know that the OT2 setting, which represent the peak frequency, doesn't perform better than the OT1 in the unit irregular wave test. And second, the unit order of a different unit WC array had an influence on the total power performance. And the buoy unit suitable for a relative short period regular wave should be placed in front, whereas suitable for a relative long period regular wave should be placed behind. And also, although the same unit array performed better, on that with the increase of the components number, the power absorption of each buoy have a negative effect when they grouping into an array. So we can try to make an array with more units, and also our future work will investigate that with more units to study this method. Maybe when the unit with 4 or 5, the same unit array, maybe 1, 1, 1, 1, 1, will perform worse than the optimized array. And we also should consider the quantity proportion of units, maybe 1, 2, 2, 3, or 1, 2, 3, 4. We have the different quantity of different components, and also numerical simulation will. Okay, thank you.
Thank you. I have one personal question. Do you have any ideas on how to conduct a numerical simulation?
We are going to use the Flow 3D software to simulate this using a CFD method.
Mm-hmm.
And we have tried to use some software using the boundary element method for this, like Aqua, and we don't think that can match the experimental result good. We use the CFD method.
Okay.
Okay.
I don't see Ilya Machevsky as participant, but maybe 2 or 3 years ago we made a very simple simulation, but it is very close to your area of interest. I can show it on screen. If you stop your presentation, I can share movie.
Okay, thank you.
Hi, Matty. Is this one of your FSI method implemented in OpenFOAM? Yeah, simple FSI.
Матвей, если ты что-то говоришь, то тебя не слышно.
Matvey have a problem with the sound, and if anyone have not any more questions, we can make a break and meet at 12:30 after 1 hour.
Okay. We come back in 1 hour.
Yes, 1 hour later.
Okay, thanks. Thanks, everyone.
Thank you, everyone.
Терялось управление, кажется.
Да,
А
у
вот
меня
сейчас
тоже что-то
слышно?
сейчас слышно, но у меня тоже что-то зависает.
У меня еще соседи начали делать ремонт, и прямо в мою стену дрелью.
Matvey, what is the reason of motion of the cylinder in your animation?
The reason is oscillating vertical power, which is produced by Kelvin-Helmholtz instability in the wake of the cylinder.
So the inflow has no waves?
No waves at inflow. It's just a resonance between Kelvin-Helmholtz instability and spring mass and
so it is a self-induced motion of...
Yes.
Okay, I see. Thank you.